Hello, Korea. Let me start by saying a heartfelt 감사합니다. Excuse my pronunciation. Thank you all for taking the time to come and join us today to listen to a little bit about VAST. I want to talk today about things that are important to us beyond just infrastructure, the real challenges that humanity faces, which is in the field of life sciences, of health, of healthcare, and the well-being of us and our children, and their children after that. The revolutions that have been happening in this space are incredible. And we at VAST Data feel that we've had a very important and crucial part to play in this journey for all of civilization. And we want to continue to play that important role within this ecosystem. So let me introduce myself a little bit. My name is Kartik. I have been with VAST Data for 2.5 years. 20 years prior to that, I was at EMC and Dell. Great companies. But VAST Data was something that attracted me. And I joined it because I found VAST was dedicated to solving the difficult problems of humanity. Not just, call ourselves VAST Data, not VAST Storage, because we really believe we are a data company and not a storage company alone. Of course, the storage platform we have designed is one that has extraordinary properties. And I'll speak some more about that and give you some feel for that as well. My past life, I used to be a physicist, so that PhD has nothing to do with computing. Unfortunately, I used to do particle physics, and I did many years of research in that arena before I joined IT. And I have to say, it's a very fulfilling career so far, because I get to solve very difficult problems, and I get to work with extremely brilliant people. And I learn every single day, and I learn from all our customers as we meet them as well. Understanding life today has really become being able to understand the enormous amount of data that's associated with understanding this very, very enigmatic thing that all of us have, which is life. Life is complex. And while all of us in high school have probably studied biology, just as I did not anticipate that the state of medical science would have advanced to this level, that we can solve problems which were previously thought unsolvable. But it's come with its own challenges. And the challenges in data and how to process this kind of data. And the data is coming from many different sources, and this is very different data from what we are traditionally used to in IT. We came from a transactionally dominated era where relational databases and transaction processing were the most important things. The data that I'm going to talk about is actually semi-structured and unstructured data. And that is growing much faster in giving rise to all the challenges that come from the growth that we see in storage. And while I'm going to be talking mainly about life sciences, many of these problems are in fact shared and common among all fields of technology as well. Let's start with looking at one of the greatest revolutions I think we have seen in the medical world, which is in the field of genomics. All of us know about the famous DNA structure, the double helix, as they call it, which is depicted in that little graphic right next to all the words here on the slide. Understanding this structure was a very long journey for humanity. In the 1990s, the world started on a very ambitious project to sequence the entire genome. That effort took almost 10 years, and it's estimated it cost probably $1 billion to do, with many thousands of very brilliant scientists working on this problem. The amazing thing is that in a short 20 years that followed after that, we can now sequence a genome in probably the matter of hours and with a cost of less than $500. In the next few years, that cost is probably going to drop to a few $100s or even less when it comes to being able to sequence this. Why is this important? Why should we care that we can do these things so effectively and so efficiently? I'll tell you a story. One of my very close friends who used to run the storage infrastructure at United Health Group in the United States, one of the largest providers on the provider side for healthcare. The story is not about his UHG or his storage, but it's actually about his wife. About 5 years ago, his wife was diagnosed with leukemia. She was fine one day. A week later, she did not have the strength to walk across the room to another chair on the other side of the room. They took her to the hospital. They diagnosed her with a very aggressive form of leukemia. And they said, you have 2 months to live. That's all the time you have. Because while this leukemia is curable, we don't know how to cure it. And the reason we don't know how to cure it is there are 50 variants of leukemia which could cause these symptoms, and we do not know which one it is. And if we could identify which one it is, we could come up with the proper medicines to be able to treat that particular variant. What they did then was to sequence her genome. And they were able to identify the gene and the specific markers that were causing this disease by looking at the structure of her genes. And from that, they identified exactly which of the 50 different variants it was, and they were able to give her the right therapeutics, the right chemo, and things like that to help her survive. I'm happy to report that 5 years after that day, she's still alive and well. To me, this is a miracle. This is the kind of miracle that data does. This is the kind of miracle that advancement in science does. Used to be that physicians and scientists would identify the parts of the genome that actually cause the disease. Today, they're realizing that the entire genome is one which is of great importance because there is a very complex interplay with the entire genome with specific genes that express certain diseases. So an era has arrived upon us where instead of just sequencing one section of the genome, what they used to call an exome, they have now started to sequence the entire genome. And this field is called whole genome sequencing. And whole genome sequencing is very data intensive. You could generate, there's about 30 times more data than just sequencing the exomes. And like, for example, a typical human genome, whole genome sequence could be 100 gigabytes in size, maybe 200 gigabytes in size, depending on the resolution and the techniques that are used. And what this does is to make the amount of data needed to be able to do large-scale population studies, to really start to develop new therapies, to start to really take on very difficult problems, such as such as curing cancer or something like that. These are ones that are now, from a technical perspective, have become technological challenges, both in storage and capacity and performance and in computational techniques to be able to do this. Along with this have come an absolute explosion of new techniques to analyze data. Renan talked about the world of AI and machine learning and deep learning, and many of these techniques are now being used even for analyzing genome sequences and starting to yield some amazing results in being able to do this. Going beyond genomics, we realize that there is a whole arena which is actually deeper than the genome, which is actually smaller than the genome. And this has to do with protein structure. Now, why would protein structure be important? Proteins, as we all know, are the building blocks of life. But let me bring to your attention, say, something like COVID-19, the pandemic we are in right now. COVID-19, the transmission vector is a virus. It's the coronavirus. And the coronavirus is basically made up of protein building blocks, specifically one particular protein, which is called the spike protein in coronavirus, is because of the shape of that protein, which is used to penetrate cell walls to infect other cells. The structure of the spike protein is of particular importance in being able to control and to be able to eradicate the effect of COVID-19 on humanity's population. But to do this, new techniques have to be developed which are much, much higher resolution than normal microscopes can deal with. Electron microscopes, of course, have higher resolution. I come from a physics background, so electron microscopy I'm no stranger to. But I also know what radiation can do. Radiation can damage tissue. So cryo-electron microscopy is a technique which was evolved to be able to look at living tissue at microscopic levels to understand the structure of proteins, to be able to advance science, to be able to improve healthcare and health quality. Turns out that the devices for these are large, complex, and expensive, and generate enormous amounts of data, absolutely enormous amounts of data. And this data not only needs to be stored, the analysis for this data now uses GPUs extensively, some for doing machine learning and some for doing mathematical operations such as Fourier transforms of the data. And all of this comes together in a field which is currently one of the hottest fields of research that exists in medical science at this point. This is several Nobel Prizes were awarded for cryo-electron microscopy. You can look it up. It is a monumental advancement in science. And this is now starting to give way to the next wave of electron microscopy, which is called electron tomography, or cryo-ET. Cryo-ET is even larger in its payloads. It is 10 times larger in the data that it generates compared to cryo-electron microscopes. And if you're wondering what cryo-electron microscopy data looks like, a typical cryo-electron microscope machine generates anywhere from 3 to 5 petabytes of data every year. That's just one machine. We work with several customers with 8 or 10 of these, and they just generate data like it's going out of style. And all that data is analyzed continually by groups of researchers, and major advancements are made here. Cryo-ET is actually going to change that even more. We are actually expecting, some of our customers are expecting as much as half an exabyte of data in the next 3 or 4 years coming from cryo-ET techniques. Another deeper area of study is around a very complex mathematical problem called protein folding. Once again, it's related to cryo-EM, that's structural biology, is to actually look at the three-dimensional structure of microscopic elements that build up life. Protein folding is a very difficult mathematical problem, again, one that's been attacked by using deep learning techniques. Google's DeepMind has evolved a set of algorithms. They call it AlphaFold. If you recollect, DeepMind also invented a deep learning model called AlphaGo. All of you know the name of Go, the game of Go. And AlphaGo was designed to play the game of Go better than anybody else, and it did. After 8 hours of playing itself, it was able to beat the world champion at Go. DeepMind turned their mind to solving difficult problems in mathematics, and they looked at protein folding. And what protein folding is even though there's a limited number of amino acids that make up a protein, the number of ways to be able to construct that and fold it are semi-infinite. And DeepMind's deep learning model was able to predict it accurately to 95% accuracy. This is hailed as one of the greatest breakthroughs in structural biology in recent times. Many say that DeepMind or AlphaFold itself should get a Nobel Prize for the advancement that it has produced in science. And most of our customers in life sciences are running AlphaFold in some place or the other. And it runs extraordinarily well on us, and I hope to give you some feel for why that is the case as we go on. The bottom line is medical science today is dominated by data and is dominated by being able to analyze data And the growth of data is not just constant, but it's almost exponential. It is growing faster than we ever anticipated that this would happen, and this is now the foundation. This is the bedrock of modern research in the medical field. So what does that mean to storage? Traditionally, what always happened was that there was a trade-off. Renan talked about this too. There's a traditional trade-off that people want high performance from storage, but they also want low cost. The subtext here, of course, is that with the amount of data being generated, we also need scale for this data. We're no longer talking about tens or hundreds of terabytes of data. We're talking about tens and hundreds of petabytes of data. How do you actually manage that? How do you actually build something which has high performance? How do you actually manage the cost of something like that? Modern AI techniques do not work with traditional hard drives. The reason is many of the workloads tend to be heavily read-intensive and random read-intensive. When you're looking at random read workloads, disk drives do not work. Mechanical disks do not work because it takes too long to find the right spot where the data is. So all-flash technologies or SSD technologies start to become standard, start to become mandatory for problems of this nature. But flash is too expensive. So people had to make a trade-off and say, okay, I am going to have 2 or 3 different kinds of storage. A small amount of extremely high-performance flash storage, and then some moderate amount of something in the middle, and then some long, slow archive. The problem with tiering is you have to constantly move data. The problem with tiering is you have to constantly tune the performance. The problem with tiering is you'd never know whether your data, which is being analyzed, is on the right tier or not when you need it. The problem with tiering is that certain classes of problems, especially using AI techniques, need democratic access to all the data at the same time. Tiering begins to fail in this kind of a scenario, and that is the number one problem that traditional methods of managing data have started to fail at this point. The compromise the industry has made, and there were 2 choices. To start to do computation at scale, you either went and said, let's look at scale-out NAS file systems. Let's look at, for example, technologies like Isilon or Cumulo or FlashBlade, all great companies, all came from a time which was a long time ago. And the model that they used was to build highly functional arrays which had a lot of enterprise features, such as replication and encryption, et cetera, built in, and were relatively easy to deploy and manage. However, they failed when it actually came to being able to also deliver the right kind of workload support for AI and HPC. They lacked some advanced technologies such as RDMA access or InfiniBand access. And last but not the least, probably the most important is when you did convert these to all-flash systems, they tended to be very expensive. The other alternative was parallel file systems. Again, a very mature technology, very extensively used in high-performance computing. And that had some of the good features that were needed to be able to analyze data at scale, such as being very scalable. You can build very large namespaces with parallel file systems, tens to hundreds of petabytes. Also, advanced techniques for connectivity using remote direct memory access, RDMA, as well as IB connectivity. However, they were far from easy to administer, far from simple to use. They definitely lacked a lot of the enterprise features. And sharing this with the scalable NAS type of solutions, they had also become prohibitively expensive when it came to all-flash systems, which now started to become more and more normal. Here's a quote from this year's BioTeam conference that was held in the US. And the gentleman who makes this quote is well known. He's very influential. Not necessarily known to be very outspoken as well. And he was very blunt in his remarks at this conference. He basically said, tiering is dead. The idea of having an archive tier or a nearline tier coupled with a fast tier is no longer a viable option because you cannot satisfy the needs of the researchers who are doing AI and machine learning to be able to do this. You need one tier. And you need that to be a permanent tier, and it needs to be a performant tier across the board. Of course, he didn't hint on what it would take to make the economics work. And that's actually the crucial point that vast data has focused on, is how do we let our customers store and process large amounts of data without breaking the bank, as the saying goes, without making things so expensive that they cannot be used. So we introduce vast data and our concept of universal storage. It's well beyond the concept now. We were founded in 2016. We are honored to have one of our co-founders, Jeff Denworth, here, whom you'll hear from later on in this afternoon. We started to ship our first product late 2018 when we came out of stealth in February of 2019. Since then, our growth has been astounding to us, especially. We have been growing 400% year over year. We exited last fiscal year at a run rate of about $300 million for software alone. If you actually looked at both hardware and software spend, we are a software company. We only monetize software. The combined total of software and hardware is closer to $600 million a year is our run rate. That is an astronomical growth rate, and I hope to give you some idea of why this platform has been so successful. We believe we are the fastest growing infrastructure company in history because we've been able to solve problems which are not solvable prior to this. So what is our secret sauce? How do we make this all happen? Why are we so different from anything that came before? The graphic to the left of the screen, which you see over here, shows on the left-hand side the classic tiering pyramid. This was driven by one and only one reason. Brennan said he had talked to hundreds of customers prior to actually starting the company. All of them said one thing. They said, we would put everything on all-flash technologies if it could be made affordable. They also said the only reason why they have multiple storage technologies and multiple tiers of storage, each one supporting different protocols, each one was supported by different vendors with no connection between these. The only reason they did that was because of cost. It was just cost prohibitive to build systems which are all flash at the scale they were looking at. It did not make sense to build multi-petascale architectures or exascale architectures with all flash. So the problem statement he gave to Brennan was, solve that problem, make flash affordable. Now, to make it affordable, we understood immediately that we also needed to solve the problem of scale, that we could not have any scaling limitations in this architecture. And then we came to a happy realization that if we could solve the cost problem with all flash and we could solve the scale problem, we didn't really have a problem with performance. You got performance for free because when you have that much solid state storage, you just got a lot of performance and you didn't really have to worry about it explicitly. It took care of itself. So our approach was fourfold. We started by a really revolutionary systems architecture to be able to solve this problem. We changed the fundamental way that scale-out systems are built in the industry. I'll speak a little more about this. And we created what we believe is the world's first shared everything cluster. And what this meant was that we did not have any limits on scale when trying to grow these systems, and we got any amount of performance that we would desire from these systems. But part of this architecture also used some very innovative techniques from Intel, some technologies from Intel, which allowed us to bring the cost down to a level which was far greater than anybody else could. Secondly, we decided deliberately that we would expose ourselves through file and object protocols, so NFS, SMB, S3, but to really build a true multi-protocol namespace. So any client running any protocol could access the same data through the protocol of their choice without having to make any compromises. Be it object presentation or file presentation, we wanted that to be universal. And we wanted to give HPC and AI level performance with enterprise NAS features, with enterprise features along with this as well. Thirdly, we realized that in addition to just making flash affordable, this had to be simple. We couldn't talk about building multi-petabyte namespaces and increasing the already complex management paradigm that existed with our customers. We have to make it easier. So simplicity was a very key, almost a ruling paradigm for us when we started to build the system. We said we have to have things that people can stand up and use easily and grow and scale as they like without having to continually add more people or to add more operational headaches. And we needed to make this resilient enough that you never needed to take an outage. No upgrade or no expansion or no full replacement for a failed hardware component should ever need the system to go down. And last but not the least, we said we want to make it simple, not just for operating and deploying these systems. We want to make it simple financially for our customers to be able to acquire this and to be able to grow this. So we introduced a revolutionary model called the Gemini model. And Teha will talk more about this, and Jeff will talk more about this, which allows us to decouple software licensing from the hardware, and in fact make it completely independent. Our software licenses are not tied to our hardware. Our maintenance is flat and constant. We warrant all our equipment for 10 years. And you only need to license what you believe you will use, not necessarily the capacity that you purchase. And the hardware capacity is purchased pretty much at cost. But I won't dwell on that. There'll be much more detail on that as we go on. What this makes it is extremely interesting in lots of ways. So we decided to build one single tier of NAS, which is actually going to bring the entire system together. I'm not going to dwell too much on details. Suffice it to say that one of the major revolutions in our architecture was that we decoupled logic, which is in the stateless container layer, from state, which is in this layer here, which has low-cost flash. Low-cost QLC flash has decent performance characteristics for read, moderate performance for writes, and terrible for endurance. That has always been the part that's been difficult to use dense flash. But the way we get around that is we use a small amount of storage class memory, which is in the form of 3D Crosspoint or Intel Optane in front of this. And this acts as a write buffer to protect the QLC from continuous writing. But on the flip side, it also helps to hold the metadata and to eliminate read and write caching in the architecture. The logic layer is, as the name states, completely stateless. Everything is in a Docker container. 100% of state is contained in the state layer or the persistence layer here. So we have the ability to scale this layer independently of the layer of persistence over here. The fact that these are stateless means we can lose these one after the other, and we still do not lose logical access to the system. The magic that makes that happen is that between the logic layer and the persistence layer, we run an NVMe over Fabric protocol layer on RDMA technology. And what that lets us do is to let every container see the entire namespace across the board. So the loss of a container means nothing. It hardly has any impact on the end user performance or availability. The remaining containers just take on the load and they continue on. And because there is no state, there is no question of any compromise in data integrity as well. These things taken together make this one of the most resilient architectures that we believe has been brought into the market. Using QLC drives allowed us to reduce the cost significantly. by 60, 70, 80% compared to other SSD technologies. But on top of that, we have very aggressive reduction of data that we do within the system itself. Way more than what you would get in most cases with just regular compression or deduplication technologies, which are fairly standard in the industry today. Our data protection scheme is also one that allows for exceptional resiliency, but very, very low overhead, as low as 2.5% overhead to be able to protect all that data. You take these three together, and now we start to see that the economics for a storage platform of this nature start to approach that of hard drive-based technologies. In fact, we generally speaking are at or below the blended cost of all the tiers that most of our customers have. And we give our customers the option of having an all-flash single namespace of infinite scale with economics to meet that for archives as well. This, we believe, is an absolute revolution in this field. So now we come to saying, how does this stack up against the technologies of yesterday? And we see that, on one side, legacy NAS does have some advantages. Good features, integrated experience, simple interfaces with file protocols, but lacking a lot of advanced kind of features as well. And parallel file systems have some advantages as well. They do support some advanced topologies. VAST supports it all. And the resilience of the system gives us an overall availability, which is significantly higher than anything you could get. When you're going to put all your eggs in one basket, like Henry Ford said, make sure that basket is strong. We make one of the strongest baskets to hold data. Our systems do not go down. And that's one of the most important things to realize in this mix as well. So I'll spend the last 15 minutes or so talking about some of our customers and what kind of work that they have done in this field. Here's a somewhat partial list of some of the life sciences customers who've entrusted their data to us and who do processing and research on a daily basis using our technologies. Some of them are very, very well known at this point. Like, for example, BioWolf. This is the National Institute of Health in the United States. It's a government organization. It has many satellite organizations as well. But the BioWolf cluster is very, very well known. It's a very large cluster, thousands and thousands of hosts. We have about 8 petabytes of capacity in that region. They run genomics workloads and cryo-electron microscope workloads literally continuously. We have seen them typically clock up to 200 gigabytes a second of throughput on days that are somewhat busy. And much of the COVID research done by the National Institute of Health is actually done on these systems over here. EMBL EBI. Now, this is another major research institute in the UK. Actually, EMBL is a consortium across Europe. They have 10 petabytes of our systems. I'll speak a little more about them. They are one of the leaders for work in genomics, for work in cryo-EM, for protein folding, et cetera. They have one of the largest protein folding databases in the world as well. Many of the subsidiaries of the National Institute of Health, National Cancer Institute, National Eye Institute, Heart, Lung, and Blood Institute, all of these are part of what we do. Even more so, private companies such as Ginkgo Bioworks, CGAT, Invitae. Many of these also do this. Walter Eliza Hall Institute in Australia, one of the leaders in both cryo-EM as well as genomics, also work in this space. So last but not the least, this MVP, the Veterans Administration, has a 1 million veteran program. And the goal is for them to sequence the genome of the roughly 1 million veterans of US wars over the ages. As I mentioned earlier, its genome is about 100 gigabytes. So this is about 100 petabytes or so, which we're talking about from a storage standpoint. All these are customers of ours, and all of them push the limits of technology in biosciences as they go forward. Let me give you some details, like Invitae. Invitae is a privately held company. Unlike, say, companies like 23andMe, which would do genealogy studies with genomes and try to figure out who your ancestors are. These people are serious medical researchers. Their high-level goals are to find a cure for cancer. And to do so, they have been doing extremely advanced genomics work for years and years. They switched their processing to start to use GPUs and to use VAST, and their processing time literally went from 24 hours to 15 minutes in being able to do this. This is what makes people like me and people at VAST very happy, because we believe that this is meaningful to the advancement of science, meaningful to the advancement of humanity, and we are contributing to one of the greatest causes that we have, to eliminate chronic disease from our population and being able to do so. Of course, this is not to say that the systems administrators were beyond thrilled with what their experience was as a system. Not only did they say that the performance is, I believe the word used was dope, a word which is more modern right now. My children have to tell me what dope meant, but apparently it means it's really good. And the performance has been incredible, but they also have said that this is so much simpler to operate as well. So great advantages in that space as well. Once again, BioWolf, I spoke briefly about some of the research work about the 8 petabytes that they'll be using to be able to run workloads for cryo-EM as well as genomics. AlphaFold apparently runs exceptionally well in these kind of environments. In fact, AlphaFold was brought to my personal attention by one of our other customers, New York University. And they reported that AlphaFold runs extremely well on VAST systems. And I became very curious, and I said, why is that the case? So I worked with them a little bit, and I reproduced that in our lab. We have a DGX-A100 in our lab, and I said, let me see what it takes to run AlphaFold in our lab machines. And to me, the gold standard for how well a workload does against VAST is to compare it against local drives, local SSD drives. So I ran it against local NVMe, and I ran that against VAST, and the results are indistinguishable. We run as good as local flash when it comes to VAST, which should be a very surprising result, because keep in mind that we are NFS. We are supposed to be slow. We're supposed to be poor performance storage. Not the case at all. When you start to operate at the same rate as flash, this becomes an exceptional value proposition. Then later on, we realized that actually this kind of workload struggles on other kind of parallel file systems by quite a bit, maybe as much as 10 times worse on other parallel file systems. That's because of the specific I/O patterns that AlphaFold uses, using a technique of mapping shared memory to data. I'm not going to go into the technical details for that, but if any of you are curious, do come and talk to me at a break, and we'll talk more about that. EMBL EBI, I mentioned them briefly. They have over 10 petabytes of our storage. And one of the things that one of their leaders shared with us when he spoke about us in public was that this had to be one of the simplest systems he's ever operated. Keep in mind that 10 petabytes is a fair amount of storage. It's a fairly big installation. He said, it's not only simple, but honestly, I don't know how to operate my dishwasher, but I do know how to use a VAST cluster. That is an enormous compliment for somebody who has years of experience in managing large amounts of data and has a lot of experience in managing data at scale, including with parallel file systems. Simplicity, as I mentioned before, and I know Jeff is going to hit on this theme too, is one of the central things that we do over here. It's not just about raw performance. It's not just about raw ease of use. It's also about supporting complex data. I mean, they have workloads which will generate hundreds of millions, even 1 billion files in a single directory, and you have to do effective processing for that. Our technology is able to work with things like that as well. This is the Veterans MVP program, like I talked about. There's like so much data that's going to be generated, even if it's exomic data, and even if it's not whole genomic data, that this is just going to grow. The techniques that are used to look at genomes are getting more and more advanced, and that means more and more data is coming here. Once again, a very laudable goal to really significantly improve healthcare and the course of humanity as we go forward within this thing. At the end of the day, what matters, I think, most is, regardless of what kind of life sciences research is being done out there, it could be in genomics, it could be in protein folding, it could be in deep learning models for protein folding, such as AlphaFold. It could be in other areas of structural biology, using codes like Reliant or Cryospark with large machines, cryo-electron microscopes or cryo-electron tomography machines. Or it could be like the Howard Hughes Medical Institute is doing with us and has been doing with us for several years, which is they're the premier institute for neuroscience in the United States. And I think they've been awarded their scientists have been awarded about 6 Nobel Prizes at this point, or more even. And when they do research like that with deep learning techniques using things like TensorFlow, all of these share one thing in common. They work best on an all-flash system. All these pipelines work the best when they have access to all the data. And clearly, from an infrastructure standpoint, they all want this to be highly, highly affordable. So I'm going to end at this point, or almost end at this point, by showing you a small video for another company called Martinos. Martinos is actually a joint collaboration between Harvard and MIT, and they do imaging. For some reason, the video is not playing. I'm going to hit this one more time, and then it plays. Beautiful.
Hi, my name is Robert Frost. I'm an assistant professor in radiology at MGH in Harvard Medical School and faculty at the Martinos Center.
Hi, I'm Paul Rains. I'm a Linux system administrator managing everything from networking, storage, desktop workstations, and HPC batch systems.
So we work on correcting problems caused by head motion in brain MRI, and with this project we can analyze a large clinical data set, which usually isn't possible because of storage limitations.
Our biggest issues in biomedical imaging storage are capacity, storage efficiency, and performance. But just as important is the ease of management of it all, making sure backups happen, and dealing with user help desk support, as well as monitoring of the storage.
In this project, we're collecting massive volumes of raw MRI data, and this is growing rapidly. All this takes up a lot of space and can be hard to analyze because of performance issues, and this led us to vast data for these needs. Now we're training machine learning algorithms on this clinical data set, and we barely need to open tickets with IT because everything just works for us.
We have lots of NFS clients. So we needed something that can support a ton of NFS clients at once. Unlike other storage solutions, VAST can handle the performance of many different clients at once without slowing down. So we're a very hybrid site, maybe 30 to 40 different research groups. Some groups are doing analysis that is mostly small file. Other groups are doing analysis that is mostly large file. So we need a system that wasn't specialized in one particular thing, that could give high performance for all of that. VAST being flash-based and having scalability with its C nodes fits the bill.
As we look to scale the volume of this clinical data set, we love the idea of using vast data. It gives us the peace of mind that we can focus on unlocking insights to ensure high quality MRI scans, even when there's head motion.
There are two things I would say. One is the technical support we've received from VAST has been excellent. They set up a Slack channel specifically for us, and their organization is always there. On a regular basis, I'm chatting with their support people about issues that we discover, or simply asking questions like, how do I do this? And they're extremely responsive. Anytime we've needed upgrades, they do that for us through a remote support tunnel. It's been the best support I've got from any vendor for any service. And then their UI, the web GUI they provide to manage the product, it's just been a pleasure to deal with. I wanted to make sure I bought a storage solution that was definitely going to work, and that would be future-proof over the next 5 years. They've also been very responsive to us and just want to be a partner.
Thank you for watching that with me. That, I think it speaks for itself. This is not an atypical experience with most of our customers. This is kind of how they've always worked with. Our strength is we are unique in our ability to build big, affordable, all-flash clusters. No scale limits, with no performance barriers, with the ease of use that one would expect, with all the features and functions that you would expect, all at a cost that is affordable. To bring the cost down, to make flash ubiquitous, that is our biggest goal. But the higher level mission that we have as a company, as I started this talk out with, is to change humanity. Is to play that part in changing humanity that's really going to change how we live, and how our planet flourishes as we go on. Do we have ambitions? Absolutely. We're aiming for well beyond the moon at this point. We want to really understand, help understand and decode brain function. We want to cure big things like cancer and disease. We know that we're not the scientists who are going to do this. We do know that the scientists need help, and our job is to make that available to them, and we are 100% dedicated to move in this direction. So with that, once again, Gam Sabmida, thank you very much for taking some time out of me.